Hello and welcome. In this video, we're going to take a look at trigonometric functions using a unit circle approach. Now, the unit circle is just a circle of radius 1 that we center at the origin. And because it has a radius of 1, the circumference of that circle is 2 pi. Now, if we start at a very specific initial point, 1, 0 on this circle, and we travel counterclockwise following the circumference of that circle, a complete rotation will end up being 2 pi. But we could stop at many other places along the way. Wherever we stop, we call that a terminal point. Well, let's take a look at the unit circle and look at some various different terminal points before we start defining what these trigonometric functions are. So here I've got a unit circle. You can see the equation x squared plus y squared equals 1. And, well, these are many different points that are on that curve. And you could see that they are points on that curve by plugging in the value for x and y from that coordinate. Make sure that, in fact, x squared plus y squared does equal 1. Well, knowing that the entire circumference is 2 pi, let's say that the distance that we travel from the initial point 1, 0 around the unit circle is some distance t. Now, t could be any number we want. In fact, this is just for t being positive. If we wanted to travel in an opposite direction, we could say that the distance would be more or less like a negative value. If we want t to be negative, then we travel clockwise. Now, since the entire circumference is 2 pi, we can divide the circle up into quadrants. If we were to travel 1/4 of the entire circumference, 2 pi, then the distance we would have traveled would be 2 pi divided by 4, which is pi over 2. And so that corresponds to this terminal point up here at the top. T equals pi over 2. If we travel a distance around the circle that far, we'll end up with a terminal point 0, 1. And if we wanted to travel halfway around the circle, half of 2 pi, that will give us t equals pi. And if we want to travel 3/4 of the way around the circle, that would be 6 pi over 4, or 3 pi over 2. If we travel 2 pi around the circle, then we'll end up back where we started. So the initial point can be listed as being t equals 0 or t equals 2 pi. Now there are some useful other terminal points here. If we were to travel a distance of pi over 6, our terminal point has coordinates √3/2 and 1/√2. If we travel a distance around the unit circle of pi over 4, well, that's 1/8 of a circle, and that leads us to the terminal point √2/2, √2/2. It's the point where x and y are equal. And if we want to travel as far as pi over 3 around the unit circle, we'll end up at a point of 1/2, √3/2. And this would be our first quadrant. So we'll label this quadrant as number 1. And then we can continue into quadrant 2. And you notice that in quadrant 2, we're going to have some symmetry. The only thing that we're going to be changing to get some other very useful terminal points here is simply changing our x coordinate to be a negative value. So we could fill in some additional distances around the unit circle in quadrant number 2. In quadrant 2, we have some distances of 2 pi over 3, 3 pi over 4, 5 pi over 6, and when we get to t equals pi, we've completed the second quadrant. Now, when we get into the third quadrant here, you'll notice that the only change from quadrant 2 to quadrant 3 is a sort of reflection of these points over the x-axis, which is going to change the y-coordinates to being negative. So in quadrant 3, we have several more terminal points depending on how far we travel into quadrant 3. So going around counterclockwise to pi, we can continue onwards and we can count up, and we'll have 7 pi over 6, 5 pi over 4, and 4 pi over 3. Traveling to the end of quadrant 3, we'll have reached a distance around the unit circle of 3 pi over 2, which is 3/4 of 2 pi. We finally get into quadrant 4. In quadrant 4, you'll see that, again, we're reflecting all of the points from quadrant 3 across now the y-axis, which is going to turn all of the x-coordinates back to positive. So, continuing onwards, we can label the distances all the way up to 2 pi. And once we get to 11 pi over 6, going a little bit farther, we end up at t equals 2 pi. So you can see, for various different distances around the unit circle, ranging from t equals 0 all the way up to one complete rotation, one complete circumference of 2 pi. Depending on the distance, you can see the terminal points. And what about if we were to travel a distance beyond 2 pi? Well, let's suppose that I wanted to travel a distance of 13 pi over 6. That would simply be 12 pi over 6, which gives me a full rotation, plus one more pi over 6, and that's going to leave me at the same terminal point as pi over 6. We say that these points are coterminal. We say that two points are coterminal if they are just some multiple of 2 pi difference. So in other words, T2 would be coterminal to T1 if T2 is simply T1 plus some multiple of 2 pi. And when we say a multiple, we mean some integer multiple. It could be adding several factors of 2 pi, or it could be subtracting several factors of 2 pi. So we just say that T2 is equal to T1 plus 2n pi, where n can be any integer. So if you think about it, having 9 pi over 4, if we were subtracting a full circle from that, which would be 8 pi over 4, then a coterminal value would be pi over 4. Pi over 4 and 9 pi over 4 are the same terminal point, root 2 over 2, comma root 2 over 2. Now, using all of these terminal points around the unit circle, we can define trigonometric functions of a real number t. Let's let t be any real number, and let's let it have a terminal point with the coordinates x and y. And if t is a number that is larger than 2 pi, that just means we'll have gone around the unit circle multiple times, but we'll still end up in one of the 4 quadrants when we're done. We'll still end up at one of these common terminal points, most likely. And if t is a negative number, if it's less than 0, then of course we're just going to go around the unit circle in a clockwise direction, and we can go around the unit circle even multiple times that direction, but we'll still end up at a terminal point in one of the 4 quadrants. So that terminal point is xy, and we define sine of t as just being the y-coordinate of that terminal point. Cosine of t is the x-coordinate. Tangent of t is a ratio of y over x, but it's undefined when x is equal to 0. Cosecant t is 1 over the y-coordinate, undefined when y equals 0. Secant t is 1 over x, undefined when x is equal to 0. And cotangent of t is x over y, undefined when y equals 0. Using the points on that unit circle, let's look at the values of these 6 trigonometric functions ranging from 0 to pi over 2. Looking at quadrant 1, we can choose these very nice distances, real numbers t. 0, pi over 6, pi over 4, pi over 3, and pi over 2. And that goes from the start to the end of quadrant 1. And in quadrant 1, the x and y coordinates are always positive. So you'll notice that none of these trigonometric values are negative. And looking at sine, since it's the y coordinate, you'll see it starts at 0 and proceeds up to 1. 0, 1 half, root 2 over 2, root 3 over 2, and 1. And cosine, of course, is the x coordinate. That's already going to start at 1 for our initial point when t equals 0. And it's going to be decreasing as we go up to the very top of the unit circle, and at pi over 2 we'll end up with an x-coordinate of 0. And by a very nice symmetry of a circle, its values are 1, root 3 over 2, root 2 over 2, 1 half, and 0. Now, tangent, cosecant, secant, and cotangent are all combinations of x's and y's. And since sine of t is the y-coordinate and cosine of t is the x-coordinate, you can actually calculate the values of tangent, cosecant, secant, and cotangent using the values of sine t and cosine t. So these are very useful identities. They're nice for being able to calculate the remaining 4 values. Tangent t, since tangent t is y over x, tangent of t is equal to sine of t over cosine of t. And it's undefined at pi over 2. It's undefined wherever we have x equal to 0. That means it's also undefined at 3 pi over 2. Now remember that cosecant is simply just 1 over y. That means it is the reciprocal of sine t. And so wherever sine t equals 0, or whenever y equals 0, cosecant t is undefined. So cosecant t is undefined at t equals 0 and undefined at t equals pi. Secant, very similar here, is the reciprocal of cosine t. So wherever cosine t equals 0, or wherever the x-coordinate equals 0, secant t is undefined. And that would happen at pi over 2, and again at 3 pi over 2. Last but not least, cotangent is just the reciprocal of tangent. And because it's the reciprocal of tangent, that means it's the reciprocal of sine over cosine, which gives us cosine t over sine t. So cotangent of t is undefined wherever tangent of t equals 0 or sine of t equals 0. And that's going to happen when t equals 0 or t equals pi. It's very useful to know that these are always true no matter what the value of t is going to be. That's why we call these identities. Doesn't matter what t is, so long as t is some real number where the function is defined, these are always true statements. Now, if you are able to at least know the values of the trigonometric ratios from 0 to pi over 2, then it can be a very quick process of finding the trigonometric ratios of values in the other quadrants. In fact, really, if you just focus on sine and cosine here, knowing those two columns, you should be able to use these identities to fill out the remaining 4. And you can remember these actually quite quickly. 0, 1/2, root 2 over 2, root 3 over 2, and 1. For sine t, if you want to be a little bit creative with that, we can actually write this as root 0 over 2, root 1 over 2, root 2 over 2, root 3 over 2, and root 4 over 2. If you have a tough time trying to memorize 0, 1/2, root 2 over 2, root 3 over 2, and 1, you might be able to use this as a little shortcut. Now, using this table and a little bit of creativity, let's come up with a method that might be useful for finding the value of a trigonometric function of any real number. We're going to use a strategy that involves something called a reference number. So depending on which quadrant we're in, this reference number is going to give us an ability to essentially just use this table to come up with a value. And then we just have to make sure that we have the correct sign. Because remember, there's a lot of symmetry in a circle. It doesn't really matter what quadrant we're in, we have the exact same coordinates just with different signs. So if you give a particular number that isn't from 0 to pi over 2, we're going to come up with something called this reference number, take a look at what the trigonometric value is, and then just correct the sign. The reference number, which we denote as t bar, is the shortest distance on the unit circle from the terminal point to the x-axis. And you can never have that distance be more than pi over 2. And we're always going to treat this as a positive distance. Now, that will be calculated differently depending on what quadrant we're in. In quadrant 1, the reference number is just equal to t. So whatever distance that we've currently traveled around is going to be exactly the same distance back to the x-axis. If we end up with a terminal point in quadrant 2, however, we haven't quite traveled far enough to reach the negative x-axis. So t bar is just going to be the remaining distance. Quadrant 3, we have now gone a little bit past the negative x-axis, and t bar is just going to be the distance backwards to the negative x-axis. And in quadrant 4, we're nearly completing a whole circle, so t bar, our reference number, is just going to be the remaining distance to get back to the positive x-axis. And now, using this reference number, we can then find a very quick process for evaluating trigonometric functions at any real number. Firstly, what we'll do is if t is some number that is greater than 2 pi, meaning we've gone around the unit circle multiple times in a counterclockwise direction, or if t is a value that's less than 0, meaning we are going around the unit circle clockwise, let's just find a coterminal value for that. And that should be a number between 0 and 2 pi. It's much easier to figure out what quadrant our terminal point is going to be in then. Now, once we know what quadrant our terminal point is in, we'll calculate the reference number. And again, we have to use the proper calculation to find the reference number. But it's always going to be a number between 0 and pi over 2. Once we have that, well, then we can go back to that table. It's pretty easy to calculate sine of pi over 6 if you already have quadrant 1 memorized. However, if now we have to change that to be actually some sort of terminal point that should have been in quadrant 3, then we just have to do a quick change and include the proper sign. And here I've got a little diagram that shows which of the functions would be positive in the 4 quadrants. So depending on which quadrant the terminal point is in, if you end up in quadrant 1, then every one of the 6 trigonometric functions is going to evaluate as a positive number. In quadrant 2, the only functions that are positive are sine and cosecant. In quadrant 3, the only functions that are positive are tangent and cotangent. And in quadrant 4, the only functions that are positive are cosine and secant. The other trigonometric functions would need to just have a negative sign included, just by symmetry. So let's try this process out and evaluate sines, cosines, tangents, cosecants, secants, and cotangents at a couple different real numbers. Okay, well, let's start with evaluating sine of 7 pi over 6. The first thing we could start off by looking at is knowing, okay, well, 7 pi over 6 is somewhere on the unit circle from 0 to 2 pi. So we can use this little notation. 7 pi over 6 is a number in the set of numbers from 0 to 2 pi. So we don't need to worry about step 1 about finding a coterminal value. But we do want to look at the reference number. And that would involve maybe just doing a quick little sketch about what quadrant we're in. If we want to count up by sixths, then we'll end up starting with 0, pi over 6, 2 pi over 6, which is pi over 3, 3 pi over 6, which is pi over 2, 4 pi over 6, which is 2 pi over 3, 5 pi over 6, and 6 pi over 6, which is pi, halfway around the circle. We're just a little bit beyond that, 7 pi over 6. That puts us into quadrant number 3. Pi over 6 is our reference angle because that's the distance that we've traveled beyond pi. So our t bar is pi over 6. This can be calculated by just simply taking 7 pi over 6 and subtracting pi. Now, looking back at our table, we see that sine of pi over 6 gives us the y-coordinate of the terminal point, which is 1/2. But, of course, that wasn't the question that we were being asked. We want to know what the value of sine of 7 pi over 6 is. Well, this is going to be exactly the same because of symmetry, but looking up at the diagram here, we know that only tangent and cotangent are positive in quadrant 3. So, sine of 7 pi over 6 is going to be equal to the negative ratio 1/2. And that's it. You could also try this on your calculator, and it should also give you the same value. Now, why don't we try looking beyond sines and cosines and trying something like tangent? Let's look at tangent of 3 pi over 4. Well, again, 3 pi over 4 is some number between 0 and 2 pi. Pretty easy to check that. 3/4 is just some number that's between 0 and 2. All right, well, then we don't have to worry about finding a coterminal angle, but what is the reference number? Well, we could use the formula, or we could just sketch a quick picture. Counting up by pi's over 4, starting at 0, we have pi over 4, 2 pi over 4, which is pi over 2, and 3 pi over 4, which puts us into quadrant number 2. Now, in quadrant number 2, we just need to travel a little bit further to get to the x-axis, and that would just be a simple distance of pi over 4 more. But if you want to use the formula, then we would have to take a look at a distance of pi minus the distance traveled, 3 pi over 4, giving us a remaining distance of pi over 4, just making sure that it's positive. And we know the tangent of pi over 4 is that special number where sine and cosine are both the same, so tangent of pi over 4 is equal to 1. That means that since in quadrant 2, only sine and cosecant are positive, tangent of 3 pi over 4 must have to equal -1. Okay, wow, let's try secant of 17 pi over 6. 17 over 6 is definitely bigger than 2. So unfortunately, 17 pi over 6 is not in the interval from 0 to 2 pi. Let's see if we can fix that. Let's take 17 pi over 6 and start by at least subtracting a full circle from that. A full circle, if we want to think about how many sixths that is going to equal 12 sixths. And then subtracting for a common denominator, that gives us 5 pi over 6, which is coterminal to 17 pi over 6. 5 pi over 6 is perfect. It is exactly what we need to be in between 0 and 2 pi. So, using 5 pi over 6 instead of 17 pi over 6 is going to make the problem a lot easier. The reference number. Well, let's just draw that diagram again. Until we start really recognizing a lot of these common numbers, it might be useful to start just drawing this picture. 5 pi over 6, if we want to count up by pi over 6, starting at 0, pi over 6, 2 pi over 6 is pi over 3, 3 pi over 6 is pi over 2, 4 pi over 6 is 2 pi over 3, and we end up at 5 pi over 6 in quadrant 2 again. The remaining distance is just going to end up being pi over 6 to get back to the x-axis. And if you wanted to calculate that in quadrant number 2, we're always going to end up taking half the circle, which is pi, subtracting the distance traveled so far, and that's how we arrive at pi over 6 remaining. Now, we happen to know secant at pi over 6, right? Well, let's say you don't. It might be a little easier just to think, well, this is going to be the reciprocal of cosine of pi over 6. And cosine pi over 6 might be a little easier to remember. This is the reciprocal of root 3 over 2. And that's going to be 2 over root 3, or if you rationalize, we end up with 2 root 3 over 3. Now, let's just think, in quadrant 2, what was positive again? Well, so it might be easiest to remember that sine is positive there. And if sine is positive, then of course cosecant is, because it's just a reciprocal. But if sine and cosecant are the only ones that are positive, then cosine and tangent are negative. If they're negative, so are secant and cotangent. We have secant here, so this must be negative. Secant of 5 pi over 6 is equal to negative 2 root 3 over 3. Now, of course, you could be computing all of these on a calculator. It is kind of handy to have a scientific calculator at all times when you're talking about taking a math course. But you know what? It is much quicker if you are able to just grab the right quadrant, grab the reference angle, and know your sines and cosines. I mean, most of the time, we're going to probably be focusing on sine, cosine, and tangent, and those are a little easier to remember. If you know those ones off the top of your head, you're quicker than a calculator that way. So we'll leave it there. There's a lot to talk about the properties of these trigonometric functions, but we'll save that for the future. Thanks for watching. I'll see you in the next video.